All right. What up, everybody? Welcome back in. Hold on one second. Let's go ahead and get the stuff loaded up here. Okay. Cool. Let me go ahead and start the recording. I'll go turn this light. Oh, hello, puppy. Hello, puppy. All right. All right. Hello, everybody. Welcome back in. My name is Michael, and I hope you're having a wonderful day. Oh, that was not my intro. Hello, everybody. My name is Michael, and welcome back to the channel. Hope you're having a wonderful day so far. Today we're going to be jumping back into MIT OpenCourseWare 6.0002, Introduction to Computational Thinking in Data Science. More specifically, we're going to be watching Lecture 10, or starting Week 10. This is going to be the continuation of Understanding Experimental Data from Week 9. This one is with Professor Eric Grimson again, and let's go ahead and get started. All right. Let's go ahead and get started.
Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Let me know how the volume is, please.
Welcome back. I hope you didn't spend time doing 6002 problem sets while eating turkey. It's not recommended for digestion. But I hope you're ready to go back into diving into material. And since it's been a week since we got together, let me remind you of what we were doing. We were looking at the issue of how to understand experimental data. Data could come from a physical experiment. We had the example of measuring the spring constant of a linear spring. Could come from biological data. Could come from social data. And what we looked at was the idea of how do we actually fit models to that data in order to understand them. So what I want to do is I want to start with that high-level reminder of what we were after. I want to do about a 5-minute recap of what we were doing last time, because it has been a while. And then we're going to talk about how do you actually validate models that you're fitting to data to understand, are they really good fits or not?
Okay.
And if you remember, and I know you spend all your time thinking about 6002, if you remember, I left you with a puzzle where I fit data to fit models to some noisy data, and there was a question of, did the model really have an order 16 fit? All right, so what are we trying to do? Remember, our goal is to try and model experimental data. And really what we want to do is have a model that both explains the phenomena underlying what we see.
Okay.
Gives us a sense of what might be the underlying physical mechanism, the underlying social mechanism.
Okay.
And can let us make predictions about the behavior in new settings. In the case of my spring, being able to predict what will the displacement be when I actually put a different weight on it than something I measured. Or if you want to think of it from a design perspective, working the other direction and saying, I don't want my spring to deflect more than this amount under certain kinds of weights. So how do I use the model to tell me what the spring constant should be for the spring I want in that case? So we want to be able to
other way to think about it.
New settings. Last piece we know is that if the data was perfect, this is easy, but it ain't. There's always going to be noise. There's always going to be experimental uncertainty. And so I really want to account for that uncertainty when I fit that model. And while sometimes I'll have theories that will help, Hooke says models of springs are linear, in some cases I don't. And in those cases, I want to actually try and figure out what's the best model to fit, even when I don't know what the theory tells me. OK, so quick recap. What did we use to solve this? We said if we got a set of observed values, my spring
Okay.
case for different displacements or for different masses, I measure the displacements.
So the sum of all the values within the
And if
set.
I had a model that would predict what the displacements should be, I can measure how good the fit is by looking at that expression right there, the sum of the squares of the differences between the observed and the predicted data. As I said, we could use other measures. We could use a first order and absolute value. The square is actually really handy because it makes the solution
Positive.
space very easy to deal
Right.
with, which we'll get to in a second.
It's always
So
positive.
given observed data, get a prediction. I can use sum of squared differences to measure how good the fit is. And then the second piece is, I now want to find what's the best way to predict the data. What's the best curve that fits the data? It's the best model for predicting the values. And we suggested last time we'll focus on mathematical expressions, polynomials.
Okay.
Professor Guttag is so excited about polynomial expressions, he's throwing laptops on the floor. Please don't do that to your laptop. We're going to fit polynomials
No laughs.
to these expressions.
No laughs.
And
Go
since
on.
the
Give him a
polynomials
laugh.
have some coefficients, the game is basically how do I find the coefficients of the polynomial that minimize that expression? And that we said was an example of linear regression.
Hey, use linear
So,
to find the best model.
Let me just
minimizes the
remind you
difference.
what linear regression says. Simple example, case of the spring. I'm going to fit a degree 1 polynomial. So that is
Use a
something
degree
of the
1
form y
polynomial
is
just
ax plus
plus
b.
b.
A and b are the free variables, the parameters I can change. And the idea is for every x, in the case of my spring, for every mass, I'm going to use that model to predict what's the displacement, measure the differences, and find the thing that minimizes. So I just want to find values of a and b that let me predict values that minimize that expression.
Okay.
As I suggested, you could solve this. You could write code to do it. It's a neat little piece of code to write. But fortunately, PyLab provides that for you. And I just want to give you the visualization of what we're doing here, and then we're going to look at examples. I'm going to try and find the best line. It's represented by two values, A and B. I could represent
line.
all possible lines in a space that has one axis with A values and the other axis with B values. Every point in that plane defines a line for me.
Okay.
Now, imagine a surface laid over this two-dimensional space where the value or the height of the surface is the value of that objective function at every point. Don't worry about computing it all, but just imagine I could do that. And by the way, one of the nice things about doing sum of squares is that surface always has a concave shape. And now the idea of linear regression is I'm going to start at some point on that surface, and I'm just going to walk downhill until I get to the bottom.
Yeah.
There will always be one bottom, one point. And once I get to that point, that A and B value tell me the best line. So it's called linear regression because I'm linearly walking downhill on this space. Now, I'm doing this for a line with two parameters, A, B, because it's easy to visualize.
So yeah, like, it's kind of hard to think about it in this two-dimensional space, but really try to think about it as like a 3D cube that's coming like up out of the screen here, right? Any point A, comma B will have some sort of third value, this Z index, or this kind of height parameter, which corresponds to, I guess, like its efficiency regarding this problem. And if we're able to find an A and B as we continue to get values that are lower and lower and lower as we walk these values inward or outward, depending on what point you start at, you continually kind of walk and get those repeatingly lower and lower values till you find a minima. And this is your answer here. And then that A and B that corresponds within this overall cube field is that value. That makes sense.
If you're a good man.
Hey, what's going on, Foaz? Hey, Smarts. Anan, how's it going? Yeah, we working hard, bro. We have so much endurance. Keep learning. It's great. Thank you so much. I appreciate you, Smarts. Be sure to tell someone you love them. I'll be back sometimes. Yeah, see you, dude. Hey, Vance, spend some time, dude. Welcome back, my guy. All right, let's keep going here.
For a line with two parameters, A, B, because it's easy to visualize. If you're a good mathematician, even if you're not, you can generalize this to think about arbitrary dimensions. So a fourth order surface in a 5-dimensional space, for example, would solve a cubic example of this. That's the idea of linear regression. That's what we're going to use to actually figure out, to find the best solution. So here was the example I used. Gave you a set of data. In about 3 slides, I'm going to tell you where the data came from, but I give you a set of data. We could fit the best line to this using that linear regression idea. And again, last piece of reminder, I'm going to use polyfit from PyLab. It just solves that linear regression problem. I give it a set of x values. I give a corresponding set of y values. Need to be the same number in each case. And I give it a dimension. And in this case, 1 says find the best fitting line. It will produce that and return it as a tuple, which I'll store under the name model 1. And I could plot it out. So just remind you, polyfit will find the best fitting n-dimensional surface, n being that last parameter there, and return it. And in a second, we're going to use polyval, which will say, given that model and a set of x values, predict what the y value should be. Apply them. Okay, so I fit the line. What do you think? Good fit? Not so much?
Not so much.
Pretty ugly.
Yeah.
I mean, you can see it's probably the best, not probably, it is the best fitting line. It's sort of,
in the middle-ish.
Variation on either side of it, but it's not a very good fit.
Yeah.
So then the question is, well,
we
why
need
not try fitting
a higher order. Yes, we need a 2-order polynomial.
Quadratic.
Quadratic.
Second order model. Y equals ax squared plus bx plus c. Run the same code, plot that out.
Yeah.
And I get that.
Here we go. Now we're cooking.
Linear model. Here's the quadratic model.
We need to fit to the appropriate model for our data.
At least by eye, looks a lot better, right?
Yeah.
It looks like it's following that data reasonably well. Okay.
Is there a catch?
I can fit a linear model. I can fit a quadratic model. What about higher order models? What about a 4th order model, an 8th order model, a 64th order model? How do I know which one's going to be best? So for that, I'm going to remind you of the last thing we used, and then we're going to start talking about how to use it further, which is, if we try fitting higher order polynomials, do we get a better fit? And to do that, we need to measure what it means for the data to fit. If I don't have any other information, for example, if I don't have a theory that tells me this should be linear in the case of Hooke, then the best way to do it is to use what's called the coefficient of determination.
Coefficient of determination. Okay, here we go.
It's a scale-independent thing, which is good. By scale-independent, I mean if I take all the data and stretch it out, this will still give me back the same value in terms of the fit, so it doesn't depend on the size of the data. And what it does is it basically tells me, with a value between 0 and 1, how well does this model fit the data. So just to remind you, in this case, the y's are the measured values. The p's are the predicted values. That's what my model is saying for each one of these cases. And mu down here is the mean or the average of the measured values. And the way to think about this is, this top expression here, well, that's exactly what I'm trying to minimize, right? So it's giving me an estimate or a measure of the error in the estimates.
So its coefficient of determination is a
and the denominator down here basically tells me
formula that can give you an r² value.
Now here's the idea.
It's a better fit.
In fact, I can get this to 0. I can get a model that completely accounts for all the variation in the estimates. That's great. It says the model
because your measured values are perfect with your predicted values.
Or r² value is
which is pretty rare, probably, right?
On the other hand, if this is equal to that, and meaning that all of the variation in the estimates accounts for none of the variation in the data, then this is 1 and this
is 0. Yeah.
So the idea is that an r² value is close to 1 is great. It says the model is a good fit to the data. R² values getting closer to 0, not so good.
Got you.
Okay. So I ran this, fitting models of order 2, 4, 8, and 16. Now you can see that model 2, that's the green line here. That's the one that we saw before. It's basically
not bad, pretty good.
Parabolic kind of arc.
I mean, red's pretty spot. I mean, red and green are like...
Look at those r² values. Wow, look at that. Order 16 fit accounts for all but 3%.
Well, yeah, but that line is almost touching almost every point. Look at it. It's like
a great fit.
Going crazy.
And you can see how it follows. It actually goes through most, but not quite all, of the data points. So
we're cooking. Let's go.
Okay? So if that's the case, if the order 16 fit is really the best fit, should we just use it? And I left you last time with that quote that says, from your parents, right? Your mother telling you just because you can do something doesn't mean you should do something. I'll leave it at that. Same thing applies here. Why are we building the model? Remember, I said 2 reasons. One is to be able to explain the phenomena.
And design it.
One is to be able to make predictions.
Yeah.
So, I want to be able to explain the phenomena. In the case of a spring, it was things like it's linear, and that gives me a sense of a linear relationship between compression and force. In this case, a 16th order model. What kind of physical process has an order 16 variation? Ugh.
Not really
Sounds
much.
a little painful. So maybe not a great insight into the process. But the second reason is I want to be able to predict future behavior of this system.
Yeah.
In the case of the spring, I put a different weight on than I've done before. I want to predict what the displacement is going to be. I've done a set of trials for an FDA approval of a drug. Now I want to predict the effect of a treatment on a new patient. How do I use the model to help me with that? One that maybe not so good currently, I want to predict the outcome of an election. Maybe those models need to be fixed from at least what happened the last time around.
Man.
But I need to be able to make the predictions.
Still the same problems happened back then or happened
explains
today.
the phenomena and lets me make predictions. Okay, so let's go back then to our example. And before I do it, let me tell you where that data came from. I actually built that data by looking at another kind of physical phenomena. And there's a lot of them, things that follow a parabolic arc.
Football
So
punts.
for example, comets. Any particle under the influence of a uniform gravitational field follows a parabolic arc, which is why Halley's Comet gets really close for a while and then goes way off into the solar system and comes back around. My favorite example, I'm biased on this, and I know you all know which team I root for, but there's Tom Brady throwing a pass against the Pittsburgh Steelers.
Oh, no, Steelers.
Center of mass of the pass follows a nice parabolic arc. Even in design, you see parabolic arcs in lots of places. They have nice properties in terms of disbursement of loads and forces, which is why architects like to use them.
Architects.
So here's how I generated the data. I wrote a little function. Actually, I didn't. Professor Guttag did, but I borrowed it. That took in 3 parameters, a, b, and c. ax squared plus bx plus c. I gave it a set of x values. Those are the independent measurements, the things along the horizontal axis. And notice what I did. I generated values given an a, b, and c for that equation.
You generate a theoretical value. Then you add in a little bit of noise.
Random.Gauss takes a mean and a standard deviation, and it generates noise following that bell-shaped curve or that Gaussian distribution. So the 0 says it's 0 mean, meaning there's no bias. It's going to be equally likely to be above or below the value, positive or negative. But 35 is a pretty good standard deviation. This is putting a lot of noise into the data.
Okay.
And then I just added that into y values. The rest of this, you can see, it's simply going to write it into a file, a set of x and y values. But this will generate, given a value for a, b, and c, data from a parabolic arc with noise added to it. And in this case, I took it as y equals 3x squared, and then b and c are 0. And that's how I generated it.
Okay.
Okay. What I want to do, I want to see how well this model actually predicts behavior. So one of the ways I could do it to say, or the question I want to ask is, whoa, if I generated the data from a degree 2 polynomial, a quadratic, why in the world is the 16th order polynomial the best fit? Puzzle. So let's test it out. I'm going to give 4, I can't count, 4 different degrees.
Okay.
Order 2, order 4, order 8, order 16. And I've generated 2 different data sets using exactly that code. Just ran it twice. It's going to have slightly different values because the noise is going to be different in each case, but they're both coming from that a y equals 3x squared equation. And the code here basically says I'm going to take those 2 data sets and basically get the x and y values out and then fit models. So I'll remind you, GenFits takes in a collection of x and y values and a list or tuple of degrees. And for each degree finds, using polyfit, the best model.
Okay.
So models 1 will be 4 models for order 2, 4, 8, and 16. And similarly down here, I'm going to do the same thing, but using the second data set. And I'm going to fit, again, a set of models. And then I'll remind you test fits, which you saw last time, I know it's a while ago, basically takes a set of models, a corresponding set of degrees, x and y values, and says for each model and that degree, measure how well that model meets the fit using that r-squared value. So test fits is going to get us back a set of r-squared values. All right, with that in mind, I've got the code here. Let's run it.
Okay.
And here we go.
Here's data set
Run
1.
that code.
That degree 16 is still dominant.
I get 2 fits. Looks good. Let's look at the values. So there's the first data set. All right. The green line still is doing not a bad job. The purple line, boy, is fitting it really well. And again, notice, there's the best fit. That's amazing. That is accounting for all but 0.4% of the variation in the data. Great fit. Order 16. Came from an order 2 thing. All right, what about the second data set? Oh, grumph. It also says order 16 fit is the best fit. Not quite as good. It accounts for all but about 2% of the variation. Again, the green line, the red line do okay, but in this case, again, that purple line is still the best fit. So I still got this puzzle. But I didn't quite test what I wanted, right? I said I want to see how well it predicts new behavior. Here what I did was I took 2 data sets, fit the model, and I got 2 different fits, one for each data set. They both fit well for order 16, but they're not quite right. Okay, so best fitting model is still order 16, but we know it came from an order 2 polynomial. So how could I really get a handle on seeing how good this model is? Well, what we're seeing here is
Comes
coming from training error.
error.
Or another way of saying it is what we're
How the
measuring
model
is
performs.
how well does the model perform on the data from which it was learned. How well do I fit the model to the training data?
Okay.
I want a small training error. And if you think about it, go back to the first example. When I fit a line to this data, it did not do well. That was not a good model. When I fit a quadratic, it was pretty decent, and then it got better and better as I went on. So I certainly need at least a small training error, but it's, to use the mathematical terms, a necessary but not sufficient condition to get a great model. I need a small training error, but I really want to make sure that the model is capturing what I'd like. And so for that, I want to see how well does it do on other data generated from the same process, whether it's weights on springs, different comets besides Halley's comets,
Okay.
different voters than those surveyed when we tried to figure out what's going to happen in an election. And I'm set up to do that by using a really important tool called validation, or cross-validation.
Cross-validate.
Let me set the stage, and then we're going to do the example. I'm going to get a set of data. I'm going to fit a model to it, actually different models, different degrees, different kinds of models. To see how well they work, I want to see how well they predict behavior under other data than that from which I did the training. So I could do that right here. I could generate the models
Generate
from one
models
data
using
set,
data set and then
but
test them on another.
the other.
Okay.
And so in fact, I had one data set. I built a set of models for the first data set. I compared how well it did on that data set, but I could now apply it to the second data set. How well does it account for that data set?
How do we
And
do that?
similarly, take the models I built for the second data set and see how well they predict the points from the first data set. What do I expect? I certainly expect that the testing error is likely to be larger than the training error because I trained on one set of data. And that means this ought to be a better way to think about how well does this model generalize? How well does it predict other behavior besides what I started with? So here's the code I'm going to use. It's pretty straightforward. All I want to draw your attention to here is, remember, models one I built by fitting models of degree 2, 4, 8, and 16 to the first data set. And I'm going to apply those models to the second data set, x vals 2 and y vals 2. And similarly, I'm going to take the models built for the second data set and test them on the first data set to see how well they fit. I know you're eagerly anticipating this. I've been setting this up for a whole week. All right, let's look at what happens when I do this. I'm going to run it, and then we'll look at the examples. So if I go back over to Python, and this code was distributed earlier, if you want to go play with it yourself, it should be the right place to do it. I am going to run that code. Now I get something a little different.
Definitely go look at this code.
At
I want to see how he did that with PyLab.
Here's model 1 applied to data set 2. And we can both eyeball it and look at the numbers. Eyeballing it, there's that green line, still generally following the form of this pretty well. What about the purple line, the order 16 degree? Remember, that's the purple line from model 1, from training set 1. Wow. Misses a bunch of points pretty badly. And in fact, look at the R-squared values. Order 2 and order 4, pretty good fit. Accounts for all but about 14, 13% of the data. Look what happened to degree 16 fit. Way down at 0.7. Last time around, it was 0.997. Ha! And what about the other direction? Taking the model built in the second data set, testing it on the first data set. Again, notice, nice fit for degree 2 and 4, not so good for degree 16. And just to give you a sense of this, I want to go back. There is the model in one case. There is the model in the other case. You can see the model that accounts for variation in one doesn't account for the variation in the other when I look at an order 16 fit.
Right, that makes sense because if you think back to these curves, when we first did the plot, each degree 16 when fitted to the original data set was fairly tailored to those individual points, right? It accounted for, less than like 1% of the variation in the entire data set. Now, when you take that model and compare it against another data set, no matter even if it's a similar degree shape as it would be for, degree 2, as these models were, had relative kind of fit, shape, it still like had such bad, comparison to the other model or the other data set, whereas a more general kind of, best case scenario with degree 2 and 4, something that's not as generalized for or niche to a data set.
Okay, so what this says is something important. Now I can see, in fact, if I look back at this, if I were just looking at the coefficient of determination, this says, in order to predict other behavior, I'm better off with an order 2 or maybe order 4 polynomial. Those R-squared values are about the same. I happen to know it's order 2 because that's where I generated it from, but that's a whole lot better than order 16. And what you're seeing here is an example of something that happens a lot in statistics. And in fact, I would suggest is often misused in fitting data to statistical samples. It's called overfitting. What it means is I've let there be too many degrees of freedom in my model, too many free parameters. And what it's fitting isn't just the underlying process, it's also fitting to the noise. Message I want you to take out of this part of the lecture is, if we only fit the model to training data, and we look at how well it does, we could get what looks like a great fit, but we may actually have come up with far too complex a model. Order 16 instead of order 2. And the only way you're likely to detect that is to train on one test set and test on a different. If you do that, it's likely to expose whether, in fact, I have done a good job of fitting or whether I have overfit to the data.
I think this comes up in like algo trading and stuff from what I've read, just some basic introduction stuff that a lot of people will fit, back test their model to a training data set and then think they have a kind of like a hit, and then when they go and test it against other data sets, it kind of just fails.
There are lots of horror stories in the literature, especially from early days of machine learning, of people overfitting to data and coming up with models that they thought wonderfully predicted an effect. And then when it ran on new data, really bit the big one. Right, so this is something you want to try and stay away from, and the best way to do it is to do validation. You can see it here. Right, the upper left is my training data, data set 1. There's the set of models. This is now taking that and applying it to a different data set from the same process. And notice, for the degree 2 polynomial, the coefficient of determination 0.86, now 0.87. The fact it's slightly higher is just accidental. But it's really about the same level. It's doing the same kind of job on the training data and on the test data. On the other hand, degree 16, coefficient of determination is a wonderful 0.996 here and a pretty awful 0.699 down there. And that's a sign that we're in not good shape.
So what's like our resolution?
Coefficient of determination drops significantly when we try and handle new data. Okay. So,
are we just trying to determine these? Like, yeah.
On the training data with a higher order model. But then do less well when we're actually handling new data. Or another way of saying it is, if I started out with, in the case of that data, a linear model that didn't fit well, and then I got to a quadratic model, why didn't that quadratic model still say the best? Why was it the case that as I added more degrees of freedom, I did better? Or another way of asking it is, can I actually get a worse fit to training data as I increase the model complexity? I see at least one negative head shake. Thank you. You're right. I cannot. And let's look at why. If I add in some higher order terms, and they actually don't matter. If I got perfect data, the coefficient will just be 0. The fit will basically say this term doesn't matter. Ignore it. And that'll work in perfect data. But if the data is noisy, what the model is going to do is actually start fitting the noise. And while it may lead to a better R-squared value, it's not really a better fit. Right, let me show you an example of that. I'm going to fit a quadratic to a straight line. Easy thing to do, but I want to show you the effect of overfitting or adding in those extra terms. So let me say it a little bit better. I'm going to start off with just I'm doing it again today. 4 simple values. 0, 1, 2, 3.
I feel you, bro. I feel you.
The y values are the same as x values. So this is 0, 0, 1, 1, 2, 2, 3, 3. They're all lying on a line. But I'm going to plot them out, and then I'm going to fit a quadratic. Y equals ax squared plus bx plus c.
1, 1, 2,
to this.
2, 3. Okay,
now I know it's a line, but I want to see what happens.
These are the actual values.
So I'm going to use polyfit to fit a quadratic. I'm going to print out some data about it.
Because the coefficients here.
And then I'm going to use polyval to estimate what those values should be.
It's going to estimate using the coefficients and plot.
And then compute the R-squared value and see what happens. All right. Okay, let me set this up better. What am I doing? I'm going to just fit it to a line. I know it's a line, but I'm going to fit a quadratic to it. And what I'd expect is, even though there's an extra term there, it shouldn't matter. So if I go to Python,
just fitting a straight line with this one, generating coefficients with polyfit here.
I'm going to run exactly that example.
And then generating a plot
look at that.
And R-squared value.
A equals 0, B is 1, C equals 0. Look at the R-squared value. Let me pull that together for you.
So our testing data perfectly fits our model.
It says in this perfect case, there's what I get. The blue line is drawn through the actual values. The dotted red line is drawn through the predicted values. They exactly line up. And in fact, the solution it finds says that higher order term, coefficient 0, it doesn't matter. So what it found was y equals x. I know, you're totally impressed. I could find a straight line. But notice what happened there. I dropped, or the system said you don't need the higher order term. Wonderful R-squared value.
Yeah.
Okay, let's see how well it predicts. Let's add in one more point out at 20. So this is 0, 1, 2, 3. That's 0, 1, 2, 3. I'm going to add 20 in there, so it's 0, 0, 1, 1, 2, 2, 3, 3, 20, 20.
So just way out here.
Again, I can estimate using the same model, so I'm not recomputing the model. The model I predicted from using those first set of 4 points.
Just
I can
takes
get the
those and
estimated
plots
y
a straight
values,
line.
plot those out, and again compute the R-squared
Plots the actual values. Gets
even adding
estimated
that
values.
point in, there's the line. And guess what?
An R-squared
Perfectly predicts it. No big surprise. So it says in the case of perfect data, adding the higher order terms isn't going to cause a problem. The system will say coefficients are 0. That's all I need. All right, now let's go back in and add in just a tiny bit of noise. Right there. 001122 and 3, 3.1. So I've got a slight
Okay, so
deviation
just a
of the
slight
value
deviation
here.
on the
Again, I can plot
fourth
them.
index
I'm going to
value.
fit a quadratic to them. I'm going to print out some information about it and then get the estimated values using that new model to see what it should look like.
Okay.
I'm not going to run it. I'm just going to show you the result. I get a really good r-squared value. And there's the equation it comes up with.
It's really close. These are the coefficients.
Not so bad, right? It's almost y equal x. But because of that little bit of noise there, there's a small second order term here and a little constant term down there. The y-squared value is really pretty good. And if you really squint and look carefully at this, you'll actually see there's a little bit of a deviation between the red and the blue line. It overshoots there, undershoots here, but it's really pretty close. All right, so am I just whistling in the dark here? What's the difference? Well, now let's add in that extra point. And what happens? So again, I'm now taking the same set of points, 0, 0, 1, 1, 2, 2, 3, and 3.1. I'm going to do 20, 20. Using the model I captured from fitting to that first set, I want to see what happens here. Crap. Oh, sorry, didn't say that. Darn. Drat. Pick up some other word. Shouldn't surprise you, right? A small variation here is now causing a really large variation up there. And this is why, in the ideal case, overfitting is not a problem because the coefficients get zeroed out. But even a little bit of noise.
So even that small deviation.
We set this up deliberately to show a big effect here, but a 3% error
Cascaded the effect way further down.
Causing a huge problem when I get further out on this curve. And by the way, there's the r-squared value. It's 0.7. Doesn't do a particularly good job.
Yeah.
Okay. So how would I fix this? Well, what if I had simply done a first degree fit? Same situation. Let's say fit a line to this rather than fitting a quadratic. Remember, my question was, what's the harm of fitting a higher order model if the coefficients will be zeroed out? We've seen they won't be zeroed out. But if I were just to have fit a line to this, exactly the same experiment, 00, 11, 22, 3, and 3.1, 20 and 20.
Yep.
Now you can see it still does a really good job of fitting. And the r-squared value is 0.9988. So again, fitting the right level of model, the noise doesn't cause nearly as much of a problem. And so just to pull that together, basically it says the predictive ability of the first order model is much better than the second order model. And
so how can we understand
that first order model?
So my question is how can we understand then, given some data sets, without actually like plotting it, visually and making a prediction about what it looks like, understand as a statistician or when doing these predictions when we need to change the degree of freedom of our model when we're experiencing too much noise or whatnot, or experiencing inconsistencies across our data sets. How can we understand, okay, what can we do to interpret that and then make those such assumptions? That's what I'm trying to figure out.
Complex model, and then we're going to amplify this. If I pick an overly complex model.
Hold on, let me catch up on some chats. Hey, what's going on, Zen? Oro, happy birthday, my boy. Welcome back in, dude. Abdullah, do you watch a course or did you ever do it to start learning? Do you watch a course or do you ever do it to start learning? Yeah, the courses are great. They just kind of help, provide some structure to the learning, and it's like it's good stuff to know, and I like doing the problem sets too. And I'm like learning a lot here on applying these kind of I've done like these kind of statistical modelings before, like in stats for scientists, like in my 3000 level stats class back in college, and definitely I've had some experience with alpha values, p values, stuff of that nature, normal curves, all that kind of stuff. But it's kind of good to actually get this insight into the angle of taking this into programming, and also applying it into Python, writing scripts to do this, and then analyzing the data with programming. So that's kind of also really nice that way. Hey Prism, how's it going? Jimmy Boats, appreciate you guys for coming in. Yeah, Eric Grimson, he's pretty smart. He definitely comes off. He doesn't definitely has a very. He's definitely very smart. Like the stuff is pretty simple for him. He doesn't really go that deep into breaking it down for like kind of us normies here. But I do like the lectures though. Hey, what's going on, Virat? How's it going? Yeah, Zen says just running again regarding my question earlier and tweaking parameters and stuff. Okay.
Amplify this model. So, take-home message, and then we're going to amplify this. If I pick an overly complex model, I have the danger of overfitting to the training data. Overfitting meaning that I'm not only fitting the underlying process, I'm fitting the noise. I get an order 16 model as the best fit when it's in fact an order 2 model that was generating it.
Yeah.
That increases the risk that it's not going to do well with new data. Not what I'd like. I want to be able to predict what's going to go on well here.
Yeah, we want to
On
be
the
able
other
to apply
hand,
that to other
so that would
data
say, boy,
sets.
just stick with the simplest possible model. But there's a trade-off here. And we already saw that when I tried to fit a line to a data that was basically quadratic. I didn't get a good fit. So I'd want to find the balance. An insufficiently complex model won't explain the data well. An overly complex model will overfit to the training data. So I'd like to find the place where the model is as simple as possible, but still explains the data. And I can't resist the quote from Einstein that captures it pretty well. Right? Everything should be made as simple as possible, but not simpler. In the case of where I started, it should be fit a quadratic because it's the right fit, but don't fit more than that because
What's that even mean?
Complex. Now, how might we go about finding then the right model? We're not going to dwell on this, but here's a standard way in which you might do it.
Okay, here we go.
Start with a low order model. Again, take that data, fit a linear model to it. Look at not only the R-squared value, but see how well it accounts for new data. Increase the order of the model. Repeat the process. And keep doing that until you find a point at which a model does a good job both on the training data and on predicting new data. And after it starts to fall off, that gives you a point where you might say, there's a good size model. In the case of this data, whether I would have stopped at a quadratic or I might have used a cubic or a quartic, it depends on the values. But I certainly wouldn't have gone much beyond that. And this is one way, if you don't have a theory to drive you, to think about how do I actually fit the model the way I would like. Let's go back to where we started. We still have one more big topic to do, and we still have a few minutes left. But let's go back to where we started. Hooke's law. There was the data from measuring displacements of a spring as I added different weights to the bottom of the spring.
Okay.
And there's the linear fit. It's not bad.
In red, with an R value of
quadratic fit.
0.88, and the quadratic is 0.95.
It's certainly got a better R-squared value.
Definitely.
That could be just fitting to the noise, but you actually can see, I think, that that green curve probably does
a pretty good
better
job
of fitting the data.
Yeah.
Well, wait a minute. Even though the quadratic fit is tighter here, Hooke says this is linear. So what's going on? Well, this is another place where you want to think about your model. And I'll remind you, in case you don't remember your physics, unless we believe that Hooke was wrong, this should tell us something. And in particular, Hooke's law says the model holds until you reach the elastic limit of the spring. You stretch a slinky too far, it never springs back. You go beyond that elastic limit. And that's probably what's happening right up there. Through here, it's following that linear relationship. Up at this point, I've essentially broken the spring. The elastic limit doesn't hold anymore. And so really, in this case, I should probably fit different models to different segments. And there's a much better fit. Linear through the first part, and another linear line once I hit that elastic limit.
Oh, okay.
How might I find this? Well, you could imagine a little search process in which you try and find where's the best place along here to break the data into two sets, fit linear segments to both, and get readable fits for both examples.
So you're saying Okay, because Hooke's law, we know that
You know,
the elasticity for the limit of of a spring, that's what, Hooke's law is determining, if I remember right back into that. It's a couple lectures ago, or last lecture, which was we watched a month ago. But as you can see, we apply this force and we get more and more distance on this spring up until the spring breaks, right? Or loses its, integrity or property of the spring itself, right? And so we get this kind of like linear kind of natural, either straight or slightly skewed line. Now, the if we're interpreting and taking this entire data set at face value and applying the model to it, you know, that doesn't really fit because it's not telling the full story. Like there is some kind of interpretation that takes place of the data, analysis of the data to understand and tell the computer, hey, there's some abnormal um, characteristics of the data where at a certain point the actual physical property of what we were measuring changed. And so the data becomes inconsistent at that point. So fitting a curve, a quadratic curve, or attempting to fit a quadratic fit in comparison to a linear fit to this model really wouldn't be accurate, as there's kind of two distinct points in this data's lifespan where the actual reading of the data really changed from consistency runs, right? And we can definitely see that here. Now, the computer doesn't know what happened here, and so it's trying to fit that model, but we can do a search over these data points, looping through them and find a point where this sort of happens and then establish a a second fit there.
and I raise it because that's the kind of thing you've also seen before. You could imagine writing code to do that search to find that good fit. Okay. That gives you a sense then of why you want to be careful about overfitting, why you want to not just look at the coefficient of determination, but see how well does this predict behavior on new data sets. Now, suppose I don't have a theory like Hooke to guide me. Can I still figure out what's a good model to fit to the data? And the answer is, you bet. We're going to use cross-validation to guide the choice of the model complexity. And I want to show you two examples.
Yeah, what if we don't know a theory?
If the data set's small, we can use what's called leave one out cross-validation. I'll give you a definition of that in a second. If the data set's bigger than that, we can use k-fold cross-validation.
I'll need to go back through and do some notes here.
Or just what's called repeated random sampling. But we can use this same idea of validating on new data to try and figure out whether the model's a good model or not.
Okay.
Leave one out cross-validation. This is just written in pseudocode, but the idea is pretty simple.
Let D be the original
Given
data
a data set, it's not too large.
We have test results
array. The idea is to walk through
the data set.
Number of trials equal to the size of the data set. And for each one, take the data set or a copy of it and drop out one of the samples. So leave one out. Start off by leaving out the first one, then leaving out the second one, leaving out the third one.
So we're going to take a slice and pop off the last one.
Each one of those training sets build the model, for example, by using linear regression.
Okay.
And then test that model on the data point that you left out. So leave out the first one, build a model on all the other ones, and then see how well that model predicts the first one. Leave out the second one, build a model using all of them but the second one, see how well it predicts the second one, and just average the results. Works when you don't have a really large data set, because it won't take too long, but it's a nice way of actually testing validation.
Yeah, this is pretty, if it's pretty big,
this is kind of brute force. If the data set's a lot bigger, you can still use the same idea, is use what's called k-fold. Divide the data set up into k equal sized chunks. Leave one of them out, use the rest to build the model, and then use that model to predict that first chunk you left out. Leave out the second chunk, keep doing it. Same idea, but now with groups of things rather than just leaving out single data points. Right. The other way you can deal with it, which has
repeated random sampling,
is to use what's called repeated random sampling. Again, start out with some data sets.
Data set is D, and N is the number of random samples.
Some number of trials. I'm going to call that K, but I'm also going to pick
so K is our number of trials
samples from the data set.
And it's usually 20 to 50%
usually, I think
of
N is,
K.
as I recall it, is somewhere between reserving 20 to 50% of the samples.
So if we're doing 100 trials, random sample would be about 20 to 50 random samples.
And in each one, pick out at random n elements for the test set, use the remainder as the training set, build the model on the training
Loop
set,
over our
and then
test.
apply that model to the test set.
Randomly select n elements
So
for the
rather
test
than
set.
doing k-fold, where I select k in turn,
Okay, we're just
this
picking
is just
stuff out.
randomly selecting which ones to pull out.
Do we put back?
So,
Is this with replacement or
I'll show you
without?
one last example. Let's look at that idea of I don't have a model here. I want to use this idea of cross-validation to try and figure out what's the best possible model. And for this, I'm going to use a different data set. The data set here is I want to model, or the task here is I want to try and model how the mean daily high temperature in the U.S. has varied over about a 55-year period, from 61 to 2015. Got a set of data. The mean, the daily high for every day of the year through that entire period. And what I'm going to do is I'm going to compute the means for each year and plot them out. And then I'm going to try and fit models to them. And in particular, I'm going to take a set of different dimensionalities, linear, quadratic, cubic, quartic. And in each case, I'm going to run through a trial where I train on one half of the data, test on the other. There again is that idea of seeing how well it predicts other data. Record the coefficient of determination, and do that and get out an average and report what I get as the mean for each of those values across each dimensionality.
Okay, got you.
Okay, here we go. Set of code that's pretty easy to see. Hopefully you can just look at it and grok it. We start off with a boring class, which Professor Guttag suggests refers to this lecture, but it doesn't. It's maybe a boring lecture, but it's not a boring class. This is a great
That was a
class.
good show.
And boy, those jokes
Come
are
on,
really
people's
awesome.
got to laugh.
Here we
Come
go.
on, those are
Simple
good
class
jokes.
that builds temperature data.
So temperature data.
Just reads in some information, splits
You're
it
not
up,
that guy,
and
pal, trust
basically
me.
records
You're
the
not
high
that
for
guy.
the day
Okay.
and the year
Yeah,
in which I got that.
Absolutely.
So for each day I've got a high temperature for that day, I'm going to give you back the high temperature and the year in which is recorded, because I don't care whether it was in January and June.
Get high and get year.
A little
okay.
function that opens up a file. We've actually given you that file if you want to go look at it. And simply walks through the file, reading it in and returning a big list of all those data objects.
Okay.
Okay. Then what I want to do is I want to get the mean high temperature for each year. Given that data, I'm going to set up a dictionary called years. I'm just going to run through a loop through all the data
Get
points
the year
where
and append
in the
the list of
dictionary
highs.
under that year, so there's the data point. I use the method getYear to get out the year. At that point, I add in the high temperature corresponding to that data point. And I'm using that nice little try except loop. I'll do that unless I haven't had anything yet for this year, in which case this will fail, and I'll simply store the first one in as a list. So after I've run through this loop, in the dictionary under the year, I have a list of the high temperatures for each day associated with it. Excuse me, and then I can just compute the average. That is, for each year in the years, I get out that value, I add them up, I get the length to divide them out, and I store that in as the average high temperature for the year.
Nice.
Now I can plot it.
Pretty simple.
Get the data, get out the information by computing those
We've
leading
definitely
yearly
done
means,
very similar
run through a
functions to
little
like
loop.
this in our own
Basically,
projects.
in the x values puts in the year, in the y values puts in
Our stock projects, our
temperature. And I can
business
do a plot.
projects, all that stuff. Done
If
stuff
I do
exactly
that-
like these kinds of functions.
I get that. I'll let you run this yourself. Now, this is a little bit deceptive because of the scale I've used here, but nonetheless, it shows in the
Good
U.S.
temperatures.
over a 55-year
Celsius.
period, the mean high day,
going up.
mean daily high has
Global
gone
warming.
from about 15.5 degrees Celsius up to about 17 and a half.
It's a pretty big increase from
it's
percentage-wise.
Now,
Pollutions, data
how could I
centers.
model this? Could I actually get a model that would give me a sense
Honestly,
of how this is changing?
like
And that's where I'm going to use
development of
cross-validation.
technology
I'm going to run through a number of trials, 10 trials.
in the computer and
Try
stuff.
and fit 4 different models: linear, quadratic,
Or I'll say
cubic,
like
quartic.
retail
And for
computer.
each of
like
these
stuff like that.
dimensions, I'm going to get out a set of R-squared values. So I'm just going to initialize that dictionary with an empty list. And now here's how I'm going to do this. Got a list of X values, those are years. I got a list of Y values, those are average highs, daily highs. I'm going to create a list of random samples.
Chill,
I haven't
Jimmy.
seen this before. Random.sample says, given this iterator, which you can think of as the collection from 0 up to n minus 1, it's going to select this many, or half of them in this case, of those numbers at random. So if I give it 0 up to 9, and I say pick 5 of them, it will at random give me back 5 of those 10 numbers with
Gotcha.
no duplicates. Ah, that's nice.
Random sample in the
now
range,
notice what I can
length
do. I'm going to
values,
set up a training,
and only 5 of
X and
them.
Y values for a training set, X and Y values for the test set, and I'm just going to run through a loop here where if this index
Half
is in
of
that list,
the X
I'll
values.
stick it in the training set. Otherwise, I'll stick it in the test set.
But you want
return them.
a range of
So
just
this
0
is a
to
really
the
nice
length.
way of at random just splitting the data set into a test set and a training set. And then finally, I can run over the number of trials I want to deal with. In each case, get a different training and test set at random. And then for each dimension, do the fit. There's polyfit on the training X and training Y values in that dimension. Gives me back a model. I could just check to see how well the training set does, but I really want to look at, given that model, how well does polyval predict the test set?
Okay.
Right? The model will say, here's what I expect as the values. I'm going to compare that to the actual values that I saw from the training set, computing that R-squared value and adding it in.
Model pilot polyfit training.
And then the last of this just says I'll run this.
The degree of freedom you want. Estimated values are
okay. Here's what happens if
coefficients, and then we're going to generate an R-squared, and we're going to generate a bunch of R-squares.
Let me again remind you what I'm doing. I've got a big set of data. I'm
Add our
going to pick
dimension.
out at random subsets of it, build the model on one part, test it on the other part. And if I run it, I get a linear fit, quadratic fit, cubic fit, and a quartic fit. And here's the standard deviation of those samples. Remember, I got a multiple trials. I got 10 trials in this case. So this gives me the average over those trials, and this tells me how much they vary.
Yeah, linear fit's definitely looking
What
pretty
can
good.
I conclude from this? Well, I would argue that the linear fit's probably the winner here.
Let's go.
It goes back to Einstein. I want the simplest possible model that accounts for it. And you can see it's got
That's for
the
this data
highest
here.
R-squared value, which is already a good sign. It's got the smallest deviation across the trials, which says it's probably a pretty good fit. And it's the simplest model.
Okay, so I got it.
So linear sounds like a pretty good fit. Now, why should we run multiple data sets to test this? I ran 10 trials of each one of these.
We don't want overfitting.
Why bother with it? Well, notice that those deviations, if I go back to it here, they're pretty good. They're about an order of magnitude less than the actual mean, which says they're pretty tight, but they're still reasonable size.
Mm-hmm.
And that suggests that while there's good agreement, the deviations are large enough that you could see a range of variation across the trials. So in fact, if I had just run one trial, I could have been screwed. Sorry, hosed. Sorry, pick your favorite word here. Hosed is a Canadian expression, in case you haven't seen it.
That's funny, yeah. So, right, because the standard deviation, even on our singular, this test data that we did for this model, shows that there is some deviation even in this. I guess that is kind of an eluding factor, or maybe like a flag to indicate to you as a data scientist to say, okay, the standard deviation, even within, not that great. Oh, these are means, right? These aren't R-squareds. These are R-squared means, I think. Right? Yeah, mean R-squareds. Right? So it's only not even super, it's close to 1, but it's not super close to 1. And we still have some deviation. So it's interesting that we need to get a better habit of analyzing these, yeah.
Here are the R-squared values for each trial of the linear fit. And you can see the mean comes out pretty well. But notice, if I'd only run one trial and I happen to get that one, oh darn. That's a really low R-squared value. And we might have decided in this case a different conclusion, that the linear fit was not a good fit. So this is a way of saying, even in random sampling, run multiple trials, because it lets you get statistics on those trials as well as statistics within each trial. So within each trial, I'm doing a whole bunch of different random samples. I'm measuring those values. And then across those trials, I'm seeing what the deviation is. And I'm going to hope my machine comes back, because what I want to do is then pull this together. What have we done? Something you're going to use. We've seen how you can use linear regression to fit a curve
to data.
2D, 3D, 6D, however big the data set is. It gives us a mapping from the independent values to the dependent values. And that can then be used to predict values associated with the independent values that we haven't seen yet. That leads naturally to both a way to measure it, which is R squared, but especially to see that we want to look at how well does that model actually predict new data, because that lets us select the simplest model we can that accounts for the data but predicts new data in an effective way.
Yeah.
And that complexity can either be based on theory, in the case of Hook, or in more likely cases by doing cross-validation to try and figure out which one is the simplest model that still does a good job of predicting out of data behavior. And with that, we'll see you next time.
Nice. Sweet. Awesome. That was lecture 5. Oh no. That was lecture 10 from oh my goodness. That was lecture 10 from MIT OpenCourseware 6.0002 Introduction to Computational Thinking and Data Science from fall 2016. That was a great lecture. I actually really liked that one, getting to actually look at the code and analyze it, and kind of make our own assumptions, and then kind of hear what Professor Grimson had to say about it. It was really good. I do want to get some more practice with PyLab and these polyfit models and see if I can just get some more familiarity with them, because we actually haven't had to use any of these functions or anything like that in the problem sets, which is pretty interesting. I thought that the problem sets would be a little bit more tailored to the lectures, but they seem to be a little bit more simple. Not overall simple. They definitely use like the same type of looping and whatnot, but we're not actually having to do any of the polyfit or PyLab imports and do these models on. We're kind of doing like a little bit more simple analysis of data in the problem sets, which is interesting. I thought they would maybe give us some more practice with this stuff, but that was a great lecture. I really liked that one. I really liked how it was kind of eye-opening here when we just slightly skewed the value during with a small measurement error in the simulation, and how drastically it skewed the results for any like cascading results down. And so your models can be affected by small deviations in data early on, for those later values, right? If you're trying to get a fit for large, complex, models or whatnot. We learned about like overfitting and stuff. So I'm gonna go back through and do some notes, kind of in some of my off time here, chilling on the couch. But thank you guys so much for being here. This was Understanding Experimental Data Continued. This was lecture 10 from MIT OpenCourseware, Introduction to Computational Thinking and Data Science. Appreciate you guys being here and joining me today. This is November the 10th, and I'll see you guys tomorrow in the next one. Peace. And I'll see you guys in the next one. All right, let me stop the recording there. Stop recording. All right, I am going to probably head out, though. I'm pretty upbeat for tonight. We've been we're going hard and heavy here. I did program in Python last night a little bit before I went to bed. What I did was I started to make this just general script to I think I was thinking about making just like an argv script or whatever, maybe just a menu script in the terminal to receive stock symbols, and so maybe we could figure out a way to display our information here, because we have a lot of good information for our current like stock engine thing that we're kind of developing, I guess. Let's kind of take a peek at some stocks. Let's go look at our boy NVIDIA. We actually bought the NVIDIA March 2026 190 call on the pullback at the pretty much almost the very bottom of that pullback. If that was the bottom, and if that was a pullback, and it's not going to continue going, hopefully. It's up 35% right now, and I probably usually would have sold by now in my normal strategies, but I just have some conviction in that one that if things continue with AI and the way they're going, I might have got that one at a really good price, and I could make some pretty good profit on that guy. So I'm gonna try. We can track NVIDIA here for some fun stuff. So let's run this here and see what we get. for this guy here. All right, so NVIDIA for this guy. So our relative volume over the past 50 days. So today our relative volume closed below. So we did peak at relative volume over the past, on that Friday. And that's maybe why we got a lot of, movement into today at that close here. People saw that volume. Now, obviously, price here with NVIDIA. Now, these aren't Bollinger Band. These aren't these bands that are set up on this one are not the Fibonacci levels. These ones are peaks and troughs. These ones are for the lows. So as you can see, this yellow one ties to this low right here, probably. Or no, it ties to this low right here, I think. No, that one wouldn't get hit. I think that this is the... Okay, past price. Oh, this is fibs. Oh, my bad. Okay, yeah, so this is the fib ones. So I did write in a Fibonacci to take in the period that you're going over some fib levels. As you can see, it kind of has some merit to some of these levels. It kind of likes to hang around some of these price levels. So we could kind of see where these like and keep an eye out for maybe if we get a pullback here and kind of don't break this all-time high, we might come back down to this 180 level. We could, if we did a Fibonacci movie for a shorter period, I bet you one would probably draw right around here. I wonder if we adjusted that, what would happen. Now on this one, this chart's interesting here. This one just kind of plots a range. So I just taken the highs of the period that you're plotting and the lows, and then also plot in, I plot the high, and then I do plot the low, and then what I also do is I plot, I find all the points within the period that meet a certain criteria for uh, isn't NVIDIA already $1 trillion company? Right? Aren't they like 3 trillion? 4.5 trillion. You think that they're only worth $1 trillion? You think they're going down? Downtown Freddie Brown, John? So on this one plots the basically like lows. And the high, one high, obviously. So it'll create that kind of boundary of your period, but also these give you some indication of where you maybe had some pivot points. So I believe that if you follow this one, the pivot point looks like it probably hit this point here or maybe here. If one of these points didn't come in lower, probably this guy here got triggered, or probably actually it was this guy. So as you can see, we had like a low that took place here. So we could identify some pullbacks, and here, as you can see, where's this one probably at? Probably like this guy here, right? So it's interesting on that front. Now this is our just NVIDIA volume over the few days. So we did peak in volume today, but our volume is kind of channeling here, which is interesting. I mean, we do have earnings coming up in a couple weeks, or at the end of next week. So I wonder if it kind of breaks back out here. But yeah, that's kind of all the plots I have for right now. It's pretty cool. Let's take a look at a little bit smaller cap. Let's take a look at my boy Elf. I am long on Elf. Don't get me wrong. We took an L. We did not take an L actually. We got out with some profits before I sold all my shares before the earnings. I took my profits and we bought back in after earnings here on that pullback. A 35, almost 40% discount. I'll take that all day long on Elf with good financials that they're going to come out with in the future. Just it was a little blip because of all this political drama and tariffs and stuff, but as you can see, a huge sell volume on this earnings day here for this relative volume, but this also could have been buy volume on the dip. We're kind of channeling down here on ELF over these closing prices. over the past little while. So if we get like a little bit of a pullback, if we get a if we kind of make a low here to kind of create this kind of wedge, and then break out of this high here for this head and shoulders continuation. Oh well, we kind of already did that here, so it's interesting. I wonder. We'll just have to keep an eye on it here. We could fall all the way down to $50 and continue, or we could kind of continue on and form a wedge here on some of these lows. Now this is my ELF one that I have. This is the low. This is the pivots chart. So as you can see, we got a pivot here on our current price. We got a spike in relative volume on that sell. So we could have got a lot of buying pressure on this day to help out with this pivot. If we maybe get a little bit more volume and some good news with the market, it could continue, or we could even fall. So we'll just keep an eye on ELF. Just slow. Honestly, my strategy with ELF is I bought quite a few shares here at this low just to kind of get some more exposure after I sold up here. Um, but it's just a slow burn, a slow DCA on this one over the next couple of quarters. And I want to see some more good results come back out on this recovery. Jimmy Boats, dude. Ask your boy Tim about Micron. Dude, I uh, I don't know what I'm on, but I called Micron almost perfectly, dude. I will actually give myself credit on this one. I'll stay pretty humble about stuff, but I'll give myself a pat on the back about this one. I told the Discord Micron was a buy on this pullback. I was personally buying Micron right around here on this plateau. Once we kind of reached up here and was successful on coming back out of this, I started buying Micron here. I told the Discord about it on this pullback here, I think. Our boy, I bought a call here as well. I sold this call like here. Look how far this has kept going. This call I sold for like fantastic money, like 100%. This call is worth like 700% now, which is crazy. But I don't really care. I'm not looking back. But yeah, Micron going nuts here. Honestly, they're putting on like $15 a day, which is pretty nuts. Like 5% a day for the past couple of days with some pullbacks in between. So, dude, it's looking pretty exponential, like gamma here. So, I don't know. We, I'm kind of regret. Tim has his shares still. I don't have mine. I'm pissed. Tim might, Tim's gonna come through. Yeah, look at this. It's the pivots. Just every pullback is just boom, boom on these pivots. Just hammering home, even on just steady volume. No real spikes, no real dips. So maybe it's just undervalued and it's just kind of catching back up, or like I don't know. It just seems really crazy though to go up like $100 and literally over $100 in 2 months is pretty nuts. Crazy move and kind of honestly slept on. I haven't seen a lot of things on Micron in the news, like in online and retail news, like in nothing. It seems pretty like slept on. Well, if you think about it, everybody's buying ridiculous amounts of GPUs, and Micron makes a piece of every GPU. That makes sense, dude. It makes sense. So maybe it's worth it to get back into Micron. Did you take a course on stocks or something? No, dude, I'm all self-taught. I don't really, I'm not saying I know a lot. I don't know much, dude, but I just kind of, I don't know. I was going to be an accounting major, so I was pretty into business finance my freshman and sophomore year until I switched to STEM. Um, my dad is a CPA, retired CPA. He had his own like firm and stuff, so I kind of grew up around finance. Um, and I was always really big into like the stock projects in school and whatnot. And so my senior year, I started really looking into stuff and options and things like that. And um, but a lot of my I don't really have any like strategies. It's mainly just my philosophy comes down. It's very simple, and it's kind of how I've kept my trading mentality. Is that I don't really view myself as anything any different than anybody else, um, and because of that, I think also that people are very easily construed about how large the world is or how large populations are. And they're often so confined to their own area they can't see that they are like everybody else, but there's so many more of them, right? So in my opinion, like that's kind of like my idea is that I'm really no different than anybody else. The things I eat, the way I talk, the things I do, the things I like to do, I have iPhone, whatever, it's no different than anybody else. And if I just have that mentality with scale, you can kind of capture where, people are going to spend their money, right? Obviously with some limitations, right? So if it's kind of wherever it's kind of simple, it's really wherever the large majority of people are spending their money, those are probably going to be the businesses that are most successful. So I kind of first started off by investing in one of my first big hits was investing in Costco a couple years back. I recognized that Costco was post Corona was pretty undervalued. It was experiencing heavy volume on an actual foot traffic day-to-day basis from my personal experiences. I, and um, the business model and the financials were looking solid. And so I, started just putting my money in there. That grew. Um, Moved that over to stuff like Nvidia, into stuff like AMD. That stuff grew. Sold that stuff. Moved over into stuff like um, what else? In Robinhood, I rode that from like 18 to like 60. Sold that. I moved stuff into. Now I've definitely taken some L's along the way, but I moved stuff into Google. I was on the Google ride before anyone pretty much else. I was buying Google at like 140, 120, all the way to 140. I was just pounding my paychecks into Google stock. Rode that all the way up to 250, 280 now. I've been trimming my Google shares. Um, Now, like, it's been pretty successful this year. Now, if I had a larger base going into, I'm only 26, so my base isn't too large. If I had a larger base going into, we'd be looking pretty nice. I mean, we're definitely looking pretty nice, but um, yeah, it's doing pretty good so far. Knock on wood. But now we're kind of back in like the Nvidia game on these dips. I've been really just playing Nvidia on these. Let me bring back up Nvidia and show you where I bought. Have been just watching these levels like a hawk and just being patient, watching the levels of where prices like to fall back down to. So I bought Nvidia on this dip here. I sold it here at 120. I bought it at this dip here. I sold it here at 130. I it kept coming down. I bought it here. I sold it up here. It kept going, right? It kept going crazy, crazy. I bought it here. Now I'm going again. Like I've just been watching these levels, and I've just been patient, and I've been waiting for when people are really fearful. Like that's also something that people say is you have to be willing to buy when people are fearful, and be fearful when people are greedy, right? Um, and it's like these simple little sayings have actually a lot of truth and a lot of merit. It's kind of funny um, that people don't really listen, right? If you kind of just listen, you know, would you mind explaining the strategy? Um, it's not really like it's kind of just like there's no like math or anything. That's what's kind of funny about it is a lot of people I'm kind of weary to say much because a lot of people might say, "Oh, you're just full of BS," or whatnot. And honestly, I probably am. I don't know, but my main thing comes down to is I buy reputable companies that are making money. I rarely am investing in things that off speculation or off of hope, right? It usually has to have actual cash flow and generation. I don't invest in crypto because it doesn't actually generate revenue and cash flow. You know, I um, Now, did I miss out on stuff? Yeah, whatever. But there's money to be made elsewhere. There's money always to be made. Um, so, but like I said earlier, as it kind of came down to, I, I I really don't feel myself as anything different than anybody else, and I often feel that the average person has a hard time um, understanding the scope and scale of population and the amount of people there are in the world. And if everybody else if the large majority of the population thinks the same way I do, behaves the same way I do, eats the same way I do, has the same kind of hobbies that I do, likes the kind of same things I do, then as long as I'm kind of investing in reputable companies that are bringing in consistent returns that the large majority of people are also putting their money into by buying their products, then it's not foolproof, but it's a pretty safe bet. Um, Now, uh, there are some smaller cap companies like I've been pretty pushing Cheesecake a lot lately. I think that they're going to be Cheesecake Factory. I think that they're cash they just generate money like crazy, and they're coming out with two new very very rapidly growing restaurants, and I think that they're going to be really successful in the future as well. Keep being successful. Same with like Elf and stuff. So I do have some of these speculations, but they still follow the principles. They're very well established companies that generate good cash flow and good revenue. Yeah, they do have some quarters maybe where they're down or whatnot, but in the grand scheme of things, the majority of the time they're up, and I like those odds. Um, and so now I did have to take about a year or two to kind of weed out that wanting to make money fast. That you do when you kind of first come into it as a trader, you do get that mentality. You do have to kind of burn it off and learn from your mistakes. Like you do have to kind of have those financial lessons where you lose money and it's kind of like you paid to learn the lesson. And I really learned that I don't mess around with short dated options. Like I do like playing options. I do like option contracts and how they move. I've really kind of gotten a good feel for understanding some of the parameters and the Greeks and IV and volume and stuff, and evaluating the contracts. But I don't mess around with short dated stuff just because of the unpredictability of politics and things like that. It's just I like to have a little bit more control. I've been, I don't really mess around with selling options. I do but it's fairly quick. I don't really hold options for that long either. So I do buy pretty far outdated options, but I'm also kind of shortly or kind of swing trading them um, off of like momentum and positive news and kind of buying in and out of these levels and whatnot. And people would say, "Oh, why don't you just keep holding and whatnot for taxes, whatnot?" But you know, no one's ever complained about paying taxes because at the end of the day, you made money. Now, if you're complaining about paying taxes, that's one thing because maybe you made too much and it sucks. But at the end of the day, you should pay your taxes. Um, we're pretty lucky. um, Anywho, yeah, that's kind of all my spiel. Sorry, I don't. Yeah, again, like I really, I'm just like an average retail guy that just does this on the side, and I watch these levels pretty much every day. It's a very large hobby of mine, um, and yeah, it's cool. And I have this private stock kind of program I've been building out. If you guys want access to this, let me know. I might make it. It's currently private on my GitHub. I might make it public just for like the Discord members as like a perk just for people in the Discord, or maybe like just channel members if I ever open that up or something. Um, but if I ever do that, it'd be super cheap. It'd be like $1. Like I would. That's why I haven't even done it because I don't want to ever charge for anything. But if I ever were to do something like that, but I don't know. I do want to give myself some kind of edge by having these kind of cool things to look at. Let's catch up on some of the stuff. Well, you think about everybody is buying ridiculous. Oh, sorry. John says you're speaking a different language to me. No worries, John. You always come in with the clutch stuff about programming, so it's about time that we come through with something, huh? Jimmy Boat says Micron has like 50 to 60% profit margins, so assuming they don't horribly mess up the fab expansion, seems like a pretty good bet. Yeah, dude. I honestly should have kept those shares, but my honestly I should have kept them, dude. Because I really had no reason to sell. Profits are profits, and it's always good to take profits, but I really had no reasons to sell because I could have taken those profits into 2026 for maybe tax purposes. Because I'm gonna get wrecked by taxes this on 2025, dude. I've already told my dad, who's my CPA. I told him I've already went into my W-2s and stuff on my W-4 or whatever, and I've already upped my tax contributions, and I've like done like one-time payments, trying to like catch up because I'm gonna get wrecked. Pounding paychecks into Google. Did you avoid all the NFT? Yeah, I didn't. I didn't touch that with like a plague, man. I avoided that like the plague. I didn't get into that. It's almost as if saying pearls of wisdom is real. Next, you think you should buying shares. Next thing you should try is buying shares and using your ownership position to get position on the board and install yourself a seat. Wrecked? Don't you have to? Not. It's not wrecked. I just have to pay a lot in taxes. Like, and a lot of it is reinvested in like my assets. So like um, I don't have like the cash for it. So it's like, yeah. I'll have to maybe do some selling. We'll see. Um, yeah, I need to get back on the business. It's been really on the back burner. We're trying to revamp it because I've been trying to build out that site and stuff to kind of have it be automated. But it's a lot of work, and I'm kind of also takes a part away from the studying and stuff. So trying to find a balance with everything. It's difficult, for sure. All right, you guys. I think I'm gonna head out for tonight. I appreciate you guys being here and hanging out with me. Please join the Discord if you want, and please consider subscribing if you aren't. My dog's looking over at me like, let's go. All right, you guys. I'll talk to you tomorrow, where we'll continue on with our studying and whatnot. So thank you guys so much for being here, and see you guys tomorrow.